Right, good evening everyone. Today's video will bear upon another topic in maths, a rather interesting question in my opinion, which is called the birthday paradox. So, in this paradox, there's a room and you are filling it with people, and you would like to know how many people would have to be in the room in total for the probability of two people sharing the same birthday. So, any two people to be a half. So, for example, you could have person A and person B sharing one birthday, but also sharing it with person C. That's totally fine, acceptable. And right, so you just want to know how many people you need to get a half as a probability. So intuitively, one might think, right, okay, so they are assuming 365 days in a year and that everyone's just has got an equal chance of being born on any random day of the year. You'd think, right, so you need around half of those slots to be filled to get two people with the same birthday, right? But actually, it's a little bit more intricate than this, and we are going to see why straight away. So let's consider the case with two people. So person A can have any birthday, right? So he can pick any birthday because there's no one yet in the room. So let's say he picks the 1st of January. So person A just happens to be born on the 1st of January. And then we add another one. So what's the probability that those two people will share one birthday? Right, it's quite low, right? Because what would happen is that person B would also have to happen to be born on the 1st of January, in which case then you'd be fine, but that is rather unlikely. As you can see, there are quite a lot of other days that person B can be born on. Right, so that was the case with two people, and just to see, we'll just check with three people. So what happens with three people? So the first person can once again pick any day of the year, and then person two has got to pick another day. It could be the same, it could not be the same. And then what's the probability of person three that he's either got his birthday on the 1st January or the same as person two? Well, then we can see through this this way to think about it. So one way to think about it is, right, so probability that a birthday is shared is the probability that person A, person B, and person C all share a birthday, right? That's possible. They're all born on the 1st of January. Or it's a probability that person A and B both share a birthday, or person B and C share a birthday, or person A and C share a birthday. So in each of these cases, we can see that the conditions for a birthday to be shared will be filled, right? So this probability works and gives us, right, so probability that they all share the same birthday. So once again, person A can choose any day of the year, person B has got to choose the same as person A, and then person C has got to choose the same as person A and person B. So this is one chance out of 365 for person B to be also born on the 1st of January or any other day, and then same as person C, right? And then probability that person A and B share the same birthday but C does not. So what's that? So person A can choose any birthday, person B can choose must choose the same birthday as person A. However, person C must not choose the same birthday as person A or B, right? Because otherwise we'd be back in the same case with person A, B, C having all sharing the same birthdays. Right, so in this case, we'd see that you'd have 1 out of 365 for person B to choose the same as person A, and then 364 chances out of 365 for person C to choose literally any other day of the year other than, for example, the 1st of January. And since all these probabilities are the same, we just multiply it by 3, giving us 0.0082%, a probability of 0.82%, or 0.0082, so which is quite low, right? But it's also already close to 1%, as you can see. And right, and so that way was a bit intricate. And another way to think about it, which is much easier in my opinion, is the probability that at least one birthday is shared is 1 minus the probability that all the birthdays are different, right? Because those all probabilities have to add to 1, and the probability that exist are either that they're all different or that they're not all different, in which case one is shared, right? So it's just logic. It's logical to think about it that way. So probability that they're all different is how does this work? So pretty much person A can choose once again any other random day of the year, so he'll choose the 1st of January, and then person B must choose any day other than the 1st, so he can choose, for example, you could choose the 1st of May, but for example, like, let's stick to the 2nd of January, and then person C must choose, has got only 363 options left, which is any other day other than 1 or 2, which gives us, once again, 0.0082 or 0.82% probability. So, right, so now that we have got this cleared up, we can start populating and add some people. Right, so using the same logic, we can easily see that with 4 people, this exact same goes, except person D must choose pretty much any other day of the year other than person A, B, or C, right? And this gives us a probability of 1.6%. With 5 people, we are already at 2.7%, so we can see we're climbing quite fast, and which is indeed the case, since we shall see immediately that with 23 people, we have crossed the halfway mark. So we only require 23 people to be in a room at once for the probability of any two to share, for the probability of at least 2 to share a birthday to be 50% or a half. Right, and here are some results I stole off Wikipedia, which clearly show the same results here. So obviously, once we go above 365 days by the pigeonhole principle, it is pretty much impossible, well, it is impossible for no people to share a birthday, since, right, so we have person A here, we are starting to fill each and every day of the year, and then once we get to the 31st of December and we have an extra person, which is person 366, they must be born on one of those days, right? Like they cannot be born on any other day, which means that they will have a colliding birthday, right, a conflicting birthday, sorry. And here you can see, well, pretty much the graph pretty easily, that as the number of people increases, then the probability that no people of matching birthday just goes decreases and decreases. And here, one more thing, if you can see at person 365, so the probability that they have no matching birthdays is literally the probability that every single person before him has got a different birthday on one of these days, and that he gets his birthday on the 31st of December, for example, or on the last remaining possible day. Right, and now we are just gonna look at it from a permutation point of view, which is pretty much the same, but I just thought it would be interesting to do it a bit with a formula. So we have a formula that I shall explain in a moment, and we want to pick a certain number from 365 with no repetitions, and where order does matter, right? Because what we want is that we do not have any people sharing a birthday, right? So how does this work? We go back to our calendar, we take, right, you can have, for example, January 1st, you can have May the 1st, you can have June the 3rd, but then afterwards these spots start filling up, and then eventually after 23 people there will be 23 days already occupied, and we want to pick, well, we want to see how many possible ways we can pick 23 days from 365, and this is done with no repetitions, and where the order does matter, which means that, for example, if person A has got the 1st of January as a birthday, and person B has got the 2nd of January as a birthday, then this is not the same as person B having the 1st of January and then person A having the 2nd of January. Right, so this formula is used with n over n factorial divided by n minus k factorial, where n this time will be 365 days, and k will be the number of people we take, aka the number of birthdays we pick, and which is going to be 23. So we can see immediately here that if we input k as 23, we get our required or desired result as 0.4923, and then 1 minus 0.4927, sorry, which is the probability that there is in fact a shared birthday, is 0.5073. And how does this where does this formula come from? Well, pretty much we can look at a pretty easy case, in which n equals 4, so we have 4 possible letters to pick from, and we want to pick 2, right? So, and order does matter. So for example, if we pick A then B, then it's going to be equal to B then A, and if order does not matter, then A and B is not equal to B and A. It'll be clear soon. And here, for example, we can literally go around here. We can pick C as the first one, and then so we can't pick C anymore, and then we can literally pick either A, B, or D. In this case, we pick D, and then same here, we pick let's pick A for first, and then we can pick B, C, or D, and we'll pick C. And how many possible ways are there to think about it? Well, in this case, we can pick any four of these, any one of these 4 different letters. So obviously we start with 4, and then since we have already picked 1, we can subtract 1, and then we have 3 more possible options, and then this gives us 12 possible combinations if order does matter, and 6 if it does not matter. So here we can see that all the possible combinations here are the ones if order does not matter, and here are the ones if they do matter. So here, for example, we can pick A, B, and then B, or we can pick A then C, A then D, or otherwise we can pick B then C, B then D, C then D, and then yeah, so pretty much here order does not matter, because A and B is going to be the same as B and A, and then here if A and B is not the same as B and A, we got all these extra possibilities that come in. And finally, we see where the formula comes from. Since we can choose 4 factorial, well, we can choose 4 possible outcomes, then we can choose 3, and then we can choose 2, and then we can choose 1. However, since we only want 2 to pick 2 numbers, we gotta obviously get rid of the last possibility, like last permutations, in which case we just simply divide by the 2 factorial, right? So the 2 and then times 1, and then we get the required answer. And then if our order does not matter, obviously then we have even less possibilities, and we just simply divide by the number of picks we want. And this is pretty much it. So I thank you guys very much for watching. I hope this was somewhat clear, and I hope this has at least cleared up your if you had any questions, like answered all your questions about this problem. If you have any questions, let me know, and otherwise I shall see you in the next video. Thank you very much.